So in this lecture I wish to derive the weak formulation for the weighted residual statement. So the weighted residual statement is W of x R of x is equal to 0. So in this statement we wish to make the summation of product of weight and residue 0 over the domain over which I perform integration. So the residue, when I assume some trial solution, it is different from the exact solution. So when I substitute my trial solution to the governing differential equation, it will not satisfy the governing differential equation. So that is said as residue. The error what I get there is said as residue. So as per the weighted residual statement, I wish to perform the product of weight and residue 0 over some domain. That is summation of weight and residue at each and every point within the domain is made 0 here. So this doesn't mean that the residue is 0 at each and every point in the domain. Just we are trying to make this product 0 on an integral sense, on an overall sense. So smaller this subdomain over which I perform this integration, better will be my results. So I wish to derive weak formulation from this weighted residual statement. I wish to take a problem for this. Let me consider a simple supported beam with uniformly distributed load throughout, with the load be Q over a length L. Okay. So the governing differential equation for this problem will be EI d power 4 d4 by dx4 minus q is equal to 0. The boundary conditions are obviously y is equal to deflection is 0 at x equal to 0 and at x equal to L. This is the essential boundary condition, displacement boundary condition or Dirichlet boundary condition, whatever. Besides this, we will have force boundary conditions. That is, the moment is 0 at x equal to 0 and at x equal to 0. That is dI d2y by dx2 is 0 at x equal to 0 and at x equal to L. So this is the force boundary condition, and this is the displacement or essential boundary conditions. So now let me substitute this differential equation with my trial solution. Y is the exact solution. I wish to substitute my trial solution into the governing differential equation and see what the residue I get. So I am going to substitute my residue into the weighted residual statement. So integral of weight into EI d4 y bar by dx4 minus q. So this is the residue. Y bar is my trial solution as against y the exact solution. So this has to be equal to 0. This has to be equal to 0. So now let me do some. Let this integration be over the entire length of the beam. So I have dx here. Okay. So now let me rearrange this 0 to L W of x EI d4 y cap dx4 dx is equal to integral 0 to L W of x q dx. Okay. So now I am going to perform integration by parts so as to reduce the continuity requirement of this trial solution. So to perform integration by parts, let me do certain things. So let this be rewritten as d by dx of d3y dx3. So this can be taken as dv and this as u. So integral. So when I perform integration by parts, it's going to be uv d2y by dx2 uv over the limit 0 to L minus integral 0 to L v d3 3. So v du So uv minus integral v du is again this one, integral 0 to L w of x q dx. Okay. So I can again perform integration by parts here. So this can be rewritten as d by dx of d2y by dx2. This can be taken as dv and this as v. So again I have u, I have minus here in front, minus u v, so d2y by dx2, I have vi here, uv over the limit 0 to L, uv minus integral v du, minus of minus is plus, so integral 0 to L, v is ei d2y by dx2 and du is d2w by dx2 dx, which is, and I have one more term here, plus w of x ei d3 by dx3 over the limit 0 to L is equal to integral w of x q dx over the limit 0 to L. So this is an interesting expression here. See, as you can obviously see here, the natural boundary condition, that is the moment being 0 at x equal 0 and x equal to L, which is the force boundary condition, appears here, arises here explicitly, naturally in the weak formulation. So rightly said, this is set as a natural boundary condition, and so this term will get vanished at x equal to 0 and as well as at x equal to L, this term is 0. And in this term, I have to perform these limits at x equal to 0 and x equal to L. I need to find this expression. One thing which we should be cautious while choosing weight function is, the weight function has to satisfy the boundary condition which the trial solution satisfies, because as we know, weight function is virtual displacement. So virtual displacement has to vanish at the prescribed displacement boundary conditions. So w of x has to be 0 at x equal to 0 and x equal to L. So this term becomes 0, this term becomes 0, this term becomes 0, this term becomes 0. I have only this term here, 0 to L ei d2 y by dx2 d2 w by dx2 dx, which is equal to integral 0 to L w of x q dx. So I am finally getting this expression. Battery bill. Soldier can problem.
Save on.
So in this expression, this is the expression what I get finally here. So the good thing about this expression is the actual governing differential equation is, if I have to substitute a trial solution into my actual governing differential equation, it should be differentiable 4 times here, the governing differential equation, because, but in this weak formulation, as the continuity demand of this trial solution has come down, here the trial solution is differentiable only twice. So if I assume a polynomial, I can go for a polynomial of lower order which can be differentiated only twice here. But if I have to only use weighted residual method, I have to go for a higher order polynomial which can be differentiated, which should be able to be differentiated 4 times here. Okay. So the continuity demand of this trial solution has come down here. This continuity demand has got added to the weight function. This has got transferred from the trial solution to the weight function here. Okay, so you can go for a low order polynomial here. Let me go for a polynomial of second order. So a0 plus a1x plus a2 x squared. So this polynomial has to satisfy the boundary conditions. So at x equal to 0, the displacement is 0. So a0 becomes 0. And at x equal to L, the displacement is 0. So this leads to a2 is equal to minus a1 by L. My dy by dx first derivative of my displacement function will be a1 plus 2a2x, and second derivative will be 2a2. So let me substitute this in the weak formulation. Okay, before that let me do certain things here. So y is equal to a1 x minus a1 by l x squared. So as I take a1 by l common, I will get x into l minus x. So in this expression I also got to know what is d2w by dx2. Further I need to know what is my weight function. So as you know, in Galerkin weighted residual method, the weight function is nothing but the function what we have in the trial solution. So we take the function in the trial solution itself as the weight function in the Galerkin formulation. So the weight here is w is equal to x into l minus x by l. So performing differentiation here, dw by dx will be equal to l minus 2x by l. d2w dx2 will be equal to minus 2 by l. And substituting this here, integral 0 to l ei, instead of d2y by dx2 I have 2a2, and instead of d2w by dx2 I will have minus 2 by l dx, which is equal to integral of x into l minus x by l, which is the weight function, into q dx performed over the limit 0 to l. So here I have only dx term, so I will have l. So minus 4a2 ei. On the right hand side I have to integrate here. So q by l comes out, we can take it outside. L into x squared by 2 minus x cubed by 3 over the limit 0 to l. So which is a q by l cubed by 2 minus l cubed by 3. So q by 6l will give me l cubed. So ql squared by 6 is what I have in the right hand side, and in the left hand side I have minus 4a2 ei by l ei. So my a2 will be minus ql squared by 24 ei. So my a1 a2 was equal to minus a1 by l. So my a1 will be ql cubed by 24 ei. So my final function will be a0 is 0, a1 x plus a2 x squared. Okay. I need to check how good this function is, how close this function is to the analytical actual deflection expression. So let me find the displacement at the center. So at x equal to l by 2, I will have q l power 4 by 48 ei minus q l power 4 by 96 ei. So 96 ei down here. So 2 will be again q l power 4 by 96 ei. I know the actual expression for quick span deflection. It's 5w l power 4 by 384 ei. It's closer to w l power 4 by 7 5 35. It's closer to 77.